Hello, good afternoon, everybody. Thank you for joining us here today. You're here for the webinar titled Smart Advancements in Industrial Linear Actuation, sponsored and presented by Thomson. So it's 2 o'clock right now, Eastern Standard Time. So I think what we're going to do is maybe wait about 30 seconds or so just to let people log in and sign in here and get access to the webinar, and then we'll get things started in just a second. Okay, welcome back here. Everybody's here for the webinar titled Smart Advancements in Industrial Linear Actuation, presented by Thomson. My name is Miles Budimer. I'm a senior editor here with Design World. So a couple of housekeeping points of order before we start here. So after the webinar is finished here today, after the live webinar, you can find it at designworldonline.com. Also, slides are available for viewing in the resource widget as well. Keep in mind that at the end of the webinar, we will have some time for a Q&A session. You can ask questions at any time throughout the webinar. There's the Q&A tab at the bottom there, so you can, if you think of a question, put it down there, and we will do our best to get to as many of those questions as we can during the Q&A at the end. Also, if you would like to tweet with us, you can tweet using that hashtag DWWebinar. We can do that throughout the duration of the webinar and after when it's finished as well. So at this time then, I'd like to take some time to present the folks that are going to be the featured speakers for today. Once again, my name is Miles Budimer, and I'm a senior editor with Design World covering motion control. And our two presenters today, let me go ahead and introduce them. First we have Travis Gilmer, who is a product line specialist for industrial linear actuators for Thomson Industries. Travis supports the ILA business while assisting sales and customer support with technical product training. Gilmer earned his Bachelor of Science in Industrial and Systems Engineering at Virginia Polytechnic Institute and State University, and he's been with Thomson for almost 3 years now. The other presenter is Håkan Persson, who is Global Product Line Director of Actuators at Thomson Industries. Håkan is responsible for all aspects of the short and long-term strategies of the global ILA business, including product roadmaps and product development. Persson earned his mechanical engineering degree from Resource Centrum in Ljungby, Sweden. I hope I said that right. And has been with Thomson for 28 years. So without further delay, I'm going to hand it over to you guys. So Håkan and Travis, it's all yours.
Thank you very much, Miles. It's me, Håkan Persson, starting the presentation here today. In the middle, I'll hand it over to Travis for a little bit more technical details. Good afternoon, everybody, and thank you for joining us today on this webinar. I'll start by making a short, brief run-through of the agenda, what we're going to talk about here today. We'll tell you a little bit about the definitions of an industrial linear actuator in our world. We'll tell you a little bit about smart actuation. Tell you a little bit about what typical applications there are where the actuators can be used. A little bit about design trends in the industry and in our world. And then we'll go over to more technical details on bus communication and design solutions. So a little bit about the definition of an industrial linear actuator in the Thomson world. It's basically an electromechanical cylinder driven by a motor, gearbox, and a screw. And typical use is basic positioning. We are talking about limited duty cycle or intermittent duty cycle. Speeds up to 3 inches a second or 75 millimeter if you're in the metric world. And we got loads up to 3,000 pounds or 13.5 kilonewton. Going over to the smart actuation, it's pretty much the onboard electronics or integrated controls making the actuators really a plug-and-play complete unit where you can get functionality like condition monitoring, low-level switching, analog or digital feedback, and also bus functionality out of the actuator, all in one package. So where are the typical applications where these type of actuators can be used? You see a couple of them on the screen here, where up left corner we're showing you a single user maintenance and or repair type of applications where you're using an actuator for opening and closing a hood over the engine compartment, for instance, on a construction type of vehicle. Over to the right, we're showing you where we have replaced the hydraulic or the manual solution on a quick attach in a skid steer in this application or in this example. Down left, we have a utility vehicle where you can see that the actuator is being used for the actuation of the dump box, for instance. And over down to the right, you're seeing an actuator being used, for instance, on a solution where you have light panels or road signs, where the actuator is being used for tilting that and being powered by solar panels, making it possible to have that application off-site where you don't really have access to power. A couple of other applications in different sectors are that you can see on the screen here. We have railroad equipment where on the picture you can see that we're controlling hatches on gravel bins on railroad cars. You can also use the actuators in that environment for rail grinding type of equipment where that fits very well. Over to the right, you have an application in what we call material handling. In this case, it's a logistic systems or a logistic train, where we have replaced hydraulic cylinders with electromechanical solutions. And in this environment where you have logistic trains and so on, the contamination that you can get out of hydraulics is a really big concern that's completely removed by using electromechanical linear actuators. Down on the slide, you can also see that these actuators can be used on other type of vehicles like emergency or rescue vehicles. Down left and to the right, you can see that this is operating a switchgear on a remote generator station in a remote location where you don't have easy access and you need to have very high reliability of this function. Moving over a little bit to what kind of trends we're seeing in these industries and industry of linear actuators and the applications I've shown you earlier. One of them is the integrated electronics or the onboard controls, making the enhanced control, giving the user enhanced controllability of the actuators. And some of the functions that you get with the onboard electronics is the low-level power switching system. You got programmable limit switches. You can synchronize several actuators, and you can also build in bus communication protocols into the actuators, not having to rely on the old type of relays externally and so on. Customers are looking for different feedback options, robust type of feedback options, either absolute or digital, and you can also get the feedback from internal or external limits, which is a little bit more simple type of feedback. A little bit more advanced feedback type of information is condition monitoring and diagnostics, where on the condition monitoring you can actually get an understanding how hard the actuator is working and how well the application is going. You can get feedback on how the voltage is being used in the actuator, and you can also get feedback on what the temperature is looking at in the different applications. And combining all of these together, you can actually get diagnostics out of the actuators, looking at what kind of or different kind of failure modes. And this is all things that we're seeing being trends, requirements in these industries. We're also seeing that customers in this environment, or users in this environment, they're having concerns, or they are requiring more and more quality standards. They're requiring more from these actuators, meaning that the actuators or the product, they need to be pre-approved to industry-wide quality standards. Everything, the product needs to be thoroughly tested. When the customer sees them, they don't need to worry about testing them in their environment, in doing field tests and so on. The actuators are really well proven before getting out to the customers. We're also seeing an increased demand for environmental protection, meaning higher requirements for seals, the IP classification up to 67, 69K static, and also IP66 dynamic. Looking at thermal trends, we're seeing trends for shock and soak temperatures, lower requirements, higher requirements, and temperature down to -40 up to +85 or even higher than that. The actuators or the product needs to be qualified very thoroughly in vibration and also salt spray testing to be able to meet the demands in the industry right now in the environment. Another trend looking out a little bit into the future is environmental awareness. Looking at the environment, we're seeing that there are more and more requirements replacing the hydraulic cylinders that are out there today when customers are thinking about environment. They are looking at less contamination from the hydraulic systems, more efficient solutions, no need to lose power when you're not operating, need to have the static load holding capabilities. A driver for this going into the future is the Kyoto Protocol that's driving more and more, as you can see on the pictures there. Load stations or charging stations for buses, for instance, to all of this to meet the increased environmental awareness. And this is really opening up the door for future or further conversion from hydraulic or pneumatic to electromechanical solutions. So looking at these trends and what it means for the electrical solution, and what you can see on the picture is a little bit the over to the left, upper left, you see the kind of the space where pneumatics are playing a role. Over to the right, you're seeing the space where hydraulics are playing a role. And it's been for a long time, and down in the middle you can see where the electrical actuators are playing a role. You can see that to be able to and what we're seeing now with the trends on converting more and more, you can see that what it's really driving is that we need to expand the bubble or the space where we have coverage for the electrical solutions to be able to do this conversion. Some other combining these trends that I've talked about and going into solutions in the future, it's really understanding what effect these trends have on the actuators and combining that all together. We're seeing that customers are requiring more compact solutions, higher power density, modular designs where they can use the same actuators and just pick and choose from options and functionality without having to change too much of their designs. Going into hydraulic or pneumatic replacement, we're seeing that the requirement for superior performance. Customers asking for higher loads, longer strokes, higher speeds, and longer life and higher efficiency to meet all of these requirements. But not only that, customers also, we need to take care of the enhanced end user experience, meaning that we're seeing more and more manual to electrical actuation. I talked about hydraulic conversion and also going into more and more automated systems by using these industrial linear actuators. And absolutely not the least, but there are more and more thoughts about thinking about the safety, where the functions like manual override, interlock functionality, and static load holding without power in is really a must to be able to meet the trends and the needs for the market here. And last but not least, we have the trend of industry 4.0, and I don't think anybody has missed that the industry 4.0 is one of the buzzwords today, and really what the industry 4.0 means, that it means connectivity between products or between actuators or products or mechanism in this industrial environment, be it actuators, machines, motors, sensor, anything. And it also means information transparency. It means that the components or the actuators or the product, they need to be able to talk to each other. They share information between each other to be able to operate together. And what's really nice about that is with our actuators coming out now, we can actually meet all those requirements that are required from Industry 4.0, and which means that going further, we will be able to provide actuators that can meet the requirements in an Industry 4.0 environment, and that's really opening a world of new opportunities for these industrial actuators. And now I'd like to hand over to Travis for a little bit more technical details. Go ahead, Travis.
All right. Good afternoon, everybody. Thanks for joining. And I'll start off with talking a little bit about control systems and smarter actuators and what we're trying to do with them and what people are looking for and what it means to have a modular control system. So typically, I guess in the past, when you were trying to control an actuator, you had some sort of outside or external control, and it was each function had its own separate part, right? So if you wanted to control speed, you'd look at an encoder. If you wanted to, look at position, you maybe look at potentiometer, or you could use the same encoder. Essentially, what this means is that each function had a different piece. So, we're looking now to integrate that. Not only integrate it into the actuator, but to integrate all those pieces together into a modular system, meaning that you can pick and place what feature you may need with that control system, but it doesn't change, what your actuator would look like. And this package allows us to kind of bundle together common features across those control systems, like monitoring current and voltage and temperature and load sensing, which is basically a function of monitoring current and voltage. So what that allows us to do is offer a standard actuator with a lot of features that were in the past customized or external or part of a separate system. So, and not only with that package that you have up top, that electronic monitoring package, you also have additional controls that you can add on to it, kind of like a building block, right? Including end-of-stroke indication, position feedback, whether that be analog or digital, dynamic braking circuits on your actuator, low-level power switching, and even something as advanced as basically a CAN bus communication protocol built into the actuator. A bit more about what that monitoring package is. I know I mentioned in bold here, you can see the features, and now I'll talk a little bit about what each one means as far as an actuator's application. If you want to monitor the current, it's checking to see how many amps are going through your system, and amperage and current rather is related to the load on the actuator. So you can sense an overload condition by monitoring that current level, and you can cut it off if something happens. So if an actuator was pushing something and then something got in the way and caused it to have to push harder, it's going to see that trip and cut it off before something happens. Whether that be a linkage or it'd be something that shouldn't be pinched by an actuator, right? So it lets you see what's going on, right, to the actuator without having to physically be there, right? You're just watching current draw, and it also gives you an added layer of safety in the application. Besides that, you have voltage monitoring. A lot of these actuators are DC. They can be powered by a battery, and if you have over time battery drains, right? So you'll be able to see that happening, right? So if it dips too low to a point where you swap out the battery, charge up the battery, whatever it needs to be, your actuator will tell you that, right? It's smart enough to see what's going on. It's interconnected. Electronic load sensing is, again, it's kind of part of that current monitoring feature, but it's allowing you to have a sense of where the load is on the actuator without an analog device, right? So it's giving you feedback electronically about what the actuator is seeing in a very physical world. On the temperature side of things, there's actually kind of two halves. Temperature compensation is on the lower half of that temperature scale, where if you have a lot of low temperatures, you'll need basically more power to push a similar load that you would at a room temperature, for example. And typically that spike in current that you'd need to have in order to push that load at low temperatures would trip the current monitoring system or the electronic load sense system. But because of that, we have there's a device that you can have on a smart actuator that'll read that low temperature and say, hey, it's low temperature, therefore you will have to push more current or allow more current to pass through. It gets rid of that nuisance trip, right? So it gives you, the result is a consistent and stable performance at low temperatures. On the high side of things, you'll have a monitoring function where it'll essentially cut off if it gets too hot, right? So you're not destroying anything or burning out a motor or doing something that electronically it would cause damage or be an unacceptable temperature to operate. Further than that, to kind of describe the enhanced control options, analog position feedback is a potentiometer, right? That's a wire-wound device. It's an absolute position device. What does that mean? That means that when you're turning off your actuator, it'll remember where it is. That way, when you start back up again, you'll remember that you're 2 inches extended and you have 6 inches to go on an 8-inch stroke actuator. So it knows where it is at all times. It's an analog feedback device, and it's absolute position, so it always will know. On the flip side of that, there's digital position feedback where it'll count basically a gear tooth sensor encoder, and it'll count pulses as it extends out or retracts back, and what that gives you is speed feedback, how many counts in a minute. You can relate that to millimeters per second of travel if you know the resolution of the encoder or the Hall effect device. It also gives you a position, but it is a relative position, which means that it's only counting. So when you turn it off, count resets back to 0. So wherever you stopped it is where 0 is going to be unless you home it, which means you'll have to retract it all the way and say this is your 0. Start counting again, and then it'll know, at 4 inches out, it's at 4 inches out physically. So it's a little bit different than the absolute position feedback device, which would remember where it is all the time. But it offers other advantages, like gives you a more easily calculated speed feedback signal. And it's also digital, which means it's a Hall effect device, which means that there's no physical contact happening. End of stroke indication is exactly that. It indicates when the actuator has reached end of stroke. It's incredibly important if you have an interlock functionality or if you have something where you need to know when you hit the end of stroke. So typically in the past, you'd use a clutch device or something like that, and it would ratchet and make a clicking noise when you hit the end of stroke or an overload. This is a much more integrated and electronic version of that. Low-level power switching is important because it gives you functionality to control your actuator with a low signal or a low current signal, which gives you the ability to run it with a PLC. It lets you integrate your actuator with your other control systems around a lot more easily. Dynamic braking prevents coast. If you can imagine an actuator in a vertical position and you are extending out and the load is trying to pull on the actuator, right? So the actuator is under tension while it's extending. We call this a helping load. If you were to stop movement, right, cut off your power, the physics behind that movement is going to want to make that actuator extend out a little bit past when you cut off power. It's called coasting, right? Same thing if you're on a car and you cut the accelerator, all of a sudden you're going to drift a little bit. Dynamic braking circuit will basically short the motor together, the motor leads together, and use that to brake the actuator to stop it from coasting after that load is encountered. So you get a much more accurate or rather precise positioning with it. It's not terribly precise. We're still on an industrial linear actuator, but it lets you know that once you cut power, you're not going to have the thing coast over time. It will stop when you want it to stop. Finally, heading off all of this is J1939 CAN bus. J1939 is a special version, rather, of CAN bus with a specific rule set I'll discuss a little bit later, but it's a standard communication for vehicles, mobile off-highway equipment, and on-highway equipment, realistically. So again, basic unit, back in the day, so to speak, you had an actuator here on the right, your power source off to the left. In between the actuator and your power source, you had a relay box or a switch box where you would have to switch your current around. This is something basically where you have a large amount of amperage that you're switching back and forth, so you have to use a relay to do that switching for you. Now we're looking to integrate that H-bridge, or rather that low-level switching circuit, inside of the actuator. So we're taking that relay and just simply putting it inside of a board on our actuator. What this gives you in the end is an actuator. It's a lot more simple. Your total system is a lot more simple. You're simply plugging an actuator into a power source. CAN, or a controller area network, or CAN bus, is a communication standard. Basically, it's a bus communication, just like USB, which is Universal Serial Bus. It's essentially a method of communicating along a similar backbone. So you have multiple devices on one large two-wire backbone that allows you to communicate with other devices and allows them to communicate with each other without having to have a controller separate for each one. So what does that mean for us? Well, we're going to integrate the actuator into a smart system, right? Where there might be other things on the bus, sensors, other things you're trying to control around with a similar control, but they're talking to each other, so they know what's going on. J1939 is a specific set of rules for CAN bus that it's governing or telling you what's happening on a commercial vehicle is where it was developed. Most automobiles have, or pretty much every automobile has, a J1939 system on it, and basically means that it's letting you set priority to the messages that are being sent back and forth, and it lets each device on that network have a defined address and priority. Therefore, it lets the system communicate effectively without having two devices fight each other for control of the bus, right? So it tells you exactly what can be on the bus, the standard, and it tells you exactly how it needs to act when it's mixing with all those other devices. That way you don't have an actuator you're trying to control fighting against a throttle control or something else that may, for that application, be more important. Some key characteristics. So J1939, or CAN bus in general, uses a two-wire differential pair of physical communication. What does that mean? That means that the wires connecting the actuators together are it's simply two wires, right? And the best thing about this is that the messaging structure of the network has incredibly good fault tolerance capability. It knows what would happen if something were to happen to that bus. So if the wiring's wrong, or if something happens to the wiring, the bus isolates it and knows what's happening. If there's a problem on the bus with one of the nodes, a node in this case can be an actuator, a control, something that's moving around on the bus that's talking to it. If something happens to it, the master CAN controller, right, the thing that's pretty much governing where everything's talking, will notice it, and if there's too many errors happening with that particular node, it'll cut it off of the bus and prevent it from overloading the bus with error-ridden information. So it's a very self-sufficient system, and it's very good for controlling multiple things at once, which is why you see it utilized in a motor vehicle that's carrying you around. A couple of other things too to mention when these things are on the same bus and fighting for control, so to speak. There's bitwise arbitration. Basically means that when each signal that's going through on the bus will either have a 1 or a 0 to determine whether or not it's dominant or recessive. And since each node on the bus has its own defined priority and its own ID, that bitwise arbitration is already pretty much predetermined. And when, say, two of them come to a junction on that bus and two messages want to get by, the bus will calculate and determine, based off of that priority and that ID, which one gets to go through first. What does that mean for equipment manufacturers like us that make stuff that go on that bus? It means that we get to tell them how it's designed in order to let them prioritize the actuator or against whatever else is on that bus. So they get to fully control every aspect of the motion, when it's moving, how it's interacting with everything else on the bus, and when it's just sitting there idle waiting for other stuff to happen. So do I still have everyone here? Okay. All communication is broadcast on that bus. So what does that mean? That means that everything that's happening to one node is seen by other nodes. That means that when you see something happen to an actuator, it's actually happening to everything else as well. So when something happens to, say, you have an actuator that's extending out and it's telling everything else on the bus that it is indeed extending out. That way, whatever else is controlling with it will know not to move if something's happening with that actuator, or will know to move because the actuator has completed its move. Some more characteristics. Again, I talked about error detection and handling and how it can handle an error happening onto that bus. The faulty nodes will be identified, and there are mechanisms in place to stop it from happening over and over again. However, if it does keep happening, they are kicked off the bus and prevented from communicating further. So it's a very good for fault tolerances, and it's very good for error handling if something were to go wrong. One undetected error gets through every 10,000 hours of operation on average. This is why you see it on an automotive application where you have a lot of moving parts talking to each other that are controlling a lot of very functional things. For an automaker, it's your wheels turning and your engine revving. For a combine manufacturer, it's what's controlling the sieve on the bottom of the combine to separate out the grain from the shaft. So it's important to not have to worry about something going wrong with the application. And if something does go wrong, it's communicated well on the bus. Finally, talk a little bit more about the exact benefits when you're putting J1939 or bus communication onto an industrial linear actuator. typically before or in the upper picture there, you can see that in order to have these actuators linked together and communicating with each other, they are each individually paired with a control, which gets expensive, it gets costly for maintenance, and it gets complicated pretty quickly. But after, if you get them on a bus, not only do you not have to worry about a control with each one, right? But with that modular control system, you get a single actuator doing multiple different tasks. So your control system gets to be centralized with that bus communication. So what does that mean for your customers? What does it mean for designers? It means that you get a lot more flexibility with putting it into the application. It cuts down on design time in general. It cuts down on design costs in general. It's easy to use because it's a standard, right? There's a J1939 database that exists for configuring out these controls and actuators, and so you can reference that as a standard of how to control and how to speak to other things on the bus. It's also easy. It's almost like a plug-and-play system. It's easy to add or replace actuators onto the bus as long as you're not overutilizing it, and it allows you to take things on and put things off with relative ease. And since there is a standard messaging, you don't have to worry about if actuator A is doing task A and actuator B is doing task B. You could switch them up and move them around without having to worry about, well, I have to control the stroke a little bit differently on this one, or I have to control the amperage draw on this one a little bit differently. It's all predetermined in that signal, so you can control it very easily through the communication network. And Miles, I think you'll pick it up from here.
Yes, I will. All right. Well, thanks, Håkan and Travis. It was a pretty good presentation, pretty informative here. So, and I'd like to remind our registrants, viewers here today. So this part is the Q&A part. So if you have any questions for either Håkan or Travis, feel free to go ahead and type them in there, and we will try to get to as many of them as we can. So throughout the presentation here, they have been coming in pretty steadily. So I'm going to try to get to some here, and like I said, see how many we can get to. And if you think of something that you want to ask them, please go ahead and submit your question. So, let's begin here. Let's see here. Let's go with let me go with this one here. So this is a question about sounds like they're asking about specific product actuators or models that were discussed in this presentation. So, like, which specific models would offer some of those features that you had mentioned in there?
Okay. Well, typically Thomson has about 3 or 4 actuators we would consider on our Smart Actuation platform. The features we discussed in detail today, namely J1939 and enhanced controllability with low-level switching and other such features, were going to be present on Thomson's WhisperTrack, Electrac HD, and Electrac throttle actuators. So we have a few different product lines, or really a product family dedicated around that Smart Actuation platform. So it's present on multiple models.
Okay, so it's something like that you could probably find more data on your website or something like that. Probably.
Absolutely, sure can.
Okay. Next question here. So this is about the sensing here, and the question is, how sensitive and quick is the sensing?
The sensing for the, I'm guessing that they're talking about the load sense on the board. How quick and how quick it reacts. So
yeah.
Typically, it's completely depending upon the application, right? If there's a heavier load and the loading scenario is such that the actuator is being pulled when it's extending, right? You have a helping load or something like that. It essentially means that it's going to be watching the entire time, but the time to sense can vary. Now, the variance is small to us on the outside, but it's not going to be something that's going to be instantaneous. I don't actually have a a hard number for you on how quick it is. It would be a better question, I guess, to answer if it was, how quick would it be in this general application. But
right.
Essentially, it's monitoring at all times. If the spike is ever encountered, it shuts it down immediately. Now, depending upon the load, that immediate shutdown on the motor may result in a less immediate shutdown on the movement of the actuator, but we're talking milliseconds here.
Okay. Okay.
And sorry, in the sensitivity, I'm sorry, one more point about that. The sensitivity is typically, the load sense is about 20 to 25% over off of a standard product that we'll send out. However, we have the ability to adjust that sensitivity to whatever you need it to be.
Okay. All right. Good info. All right. So here's a question that's probably a little bit more of like a general or basic type of question, but it's a question about duty cycle. It says, what is duty cycle, and what may happen if I exceeded the duty cycle, I guess. So I guess just a generalized explanation of maybe what duty cycle is.
Sure. Yeah, kind of back to basics for just actuators in general, probably something we should have touched on. But a duty cycle is basically a measure of on time versus total time. And it basically, for our actuators or for industrial linear actuators in general, it's somewhere between 20 to 25%. So for a quick example, if the move that your actuator needed to do took 15 seconds, then after that 15 seconds, you would have to not move, or the actuator would have to be in a rested state for 45 seconds before you could get to move again without sacrificing cycle life of the actuator or risking tripping the thermal compensation on the board or on the motor, depending upon which actuator you use. So you can only be moving 25% of the time that you have it in operation.
Okay. Yeah, that sounds like that's a good answer. I mean, it's one of those very simple types of questions, but if you haven't really worked with it too much, then duty cycle can be kind of a mystery, I guess, right?
One of those buzzwords.
But I think just to comment on that one here from my side, Håkan here as well. The second part of the question: what happens if you exceed the duty cycle? And pretty much all of our actuators are protected for exceeding the duty cycle, and so pretty much what happens is that the actuator pretty much protects itself, and so it doesn't, you don't ruin the product or so, but it just makes it inoperable because there is onboard security for the actuator if you exceed the rate of duty cycle.
Okay, good. That's a good point too. All right, so here's another one. This is kind of about servicing, I think, and maintenance. It says, so the question is, do gears, bearings, and screws need any kind of special servicing or greasing?
At least our actuator product line is maintenance free.
Okay.
So sealed actuator, typically you're not going to be, or for an industrial linear actuator, you're not going to have to worry about regreasing a screw or regreasing the gears. Once it's reached its rated life, not something you'll be able to take apart, reservice, and put back together again.
Okay. All right, so here's switching gears a little bit here. Here's a question about specific applications, I guess. The question is, do you have any actuators in stainless steel that would be used in, like, the food industry, for instance, food processing?
Not in our industrial line. There are kind of a different question because stainless steel is good for the food industry, but not always necessarily necessary, right? So we've had applications with one of our actuator product lines where it's been in a food-grade application. It's because of its high sealing. It has a lot of ingress protection. So if it has a high ingress protection rating, which essentially means that dirt or dust or water is not going to get into the actuator, then it's feasible that it's not coming out. So you get a sealed actuator package. I would recommend really, we don't really have a food grade actuator. However, we're certainly capable in those applications, and linear actuators in general are certainly capable in those applications. So I would want to take a look at the application in general and decide from there, or let the manufacturer decide whether or not that an E-coated actuator, for example, is going to do well in a food grade application.
All right. So here's a question too about some of these specific actuators. I think the question is, what kind of cycle life does the actuator have? I don't know if I'm not sure if that was mentioned or not, but
the so standard rating for an actuator, and there are some outliers, right, with some specific ones that we build, but typically it's about 40,000 cycles at full rated load. And that 40,000 cycle life rating is also done with a resisted load in both directions. So what does that mean? That means when we're testing it for life cycles, we're pushing against the actuator when it's extending, right? It's in a compressive load when it's extending, and it's in a tensile load, or we're pulling away from it when it's retracting. So that way both sides of the ball screw inside are being worn evenly. So if you always have a resistive load one way and a helping load the other way, or then you're only hitting one side of that screw, then your life rating is cut in half. There's also a pretty big limitation with the motors used inside of electric actuators. Over time, the brushes on a DC motor will wear out, and you won't have enough basically amperage to push anything load-wise on the actuator. That typically happens after about 200 to 300 on-time hours for the motor. That for the speeds that we're offering our actuators, that still allows you to get the 40,000 cycles at rated load. Again, there's some outliers. We have some that are designed for 500,000 cycles, like a throttle actuator. And we have some that are lower, that are also a lot lower load and lower speed. So.
Okay. All right. So let's see. The next question here. So this is a question that says, how is your actuator's weight compare, or how does the actuator weight compare to other companies or other suppliers with the same types of loads and current, moments, capacity, and duty cycles? So some of those variables.
Hawking can confirm with me here. I mean, we're typically at or around where pretty much everyone else is. There's some components that we'll have in ours that others don't, that have the same load capacity. We make two actuators that have the exact same load capacity that are different weights, just because of the fact that they use different screws inside and different componentry inside. So if we get an identical actuator, I guess, from across the market, that we're going to be comparable or competitive with that weight as well.
Yeah, I would say that to complement that, this weight hasn't really been a design criteria for us. It's to us robustness and reliability is more important than the weight of the actuator. So we haven't really focused on designing low weight actuators.
Okay. All right. Let's see. So this is a question about bus voltage. So this one asks, does bus voltage have any effect on motor performance? I know if I have a high bus voltage, I can run higher speed. Any other impacts on higher bus voltage?
Okay. So the board will regulate the voltage of your bus. So if you're trying to run it at high line and trying to get it to go faster with essentially a PWM setup, that board will regulate that. So if you try to give a 24-volt actuator 28 volts, the board's going to bring it down and treat it like it's getting 24 volts. So your high bus voltage shouldn't affect the actuator unless you trip it too high, in which case it'll trip that load, the voltage load sense, which will tell you have a parameter error on your bus. It's all detailed in the installation manual for our products that use that J1939 bus configuration.
Okay. Okay. Let's see here. So see if we can take another question or two here. What about let's see. Can a duty cycle be increased by oversizing the actuators? That's another one.
It's a great question. So duty cycle is entirely dependent upon load, just as much as it is dependent upon the motor that you have inside of the actuator. So if you're not using a high load on an actuator, then you're not pulling a lot of amps through the motor, which typically means that your motor's not getting as hot, right? So if you have let's just say for sake of easy explanation, let's say you have a 1,000-pound actuator and you're only using 200 pounds, you're only putting 200 pounds of loading on it, then your duty cycle can certainly be higher than 25%. It's still good to rest your actuator. You're not going to be able to get continuous use out of these things because simply your gear motor will wear out after, over time. But if you're keeping lower amperage on the motor with low loads, then you're effectively giving yourself a higher duty cycle rating. It's just we rate our actuators at fully rated load, so we therefore can only give you a 25% rated duty cycle in order to achieve the life rating of the actuator.
Okay. Okay. So here's a question about the load here for one of the actuators here. It says the load in your catalog on the Electrac HD is 10,000 newtons, but here you specify 13,500 newtons dynamic. Does that make sense?
Yep. So we did that on purpose.
Oh, okay.
So we're marketing that actuator in particular as a hydraulic solution, or we're trying to expand that bubble as Hawken was talking about, right? So.
Okay.
The original specs of the current catalogs that are released out right now go to 10,000 newton. 13.5 kilonewton is on the horizon for us. Not published yet, but certainly in the design.
Okay, gotcha. Okay. All right. So here's a question about power, basically. Something about power draw. How much power do the electronics in the actuators draw? For instance, when they're idle, or even on startup, so when they start.
Great. So there's a couple of things to consider here, and I think the more important one is to consider startup, because you have something called an inrush current, and that just typically means that for some of the higher electronics, you'll have a large burst for a very short amount of time of amperage to consider, and some controls need to be aware of that. Now, for some of the more, some of the fancier versions, right, we'll have a soft start, which will limit that inrush current down, but typically it's like 1.5 times the rated current of the actuator. However, and also low-level switching is a good way to address low-level current. So that could, something with low-level switching, you could use a 350-watt power supply where you would use a 500-watt power supply. But that's to tolerate for that inrush. Again, idle, we actually have a sleep mode that we'll utilize, which is really, really low amperage, 30 to 40 milliamps for a 24-volt actuator, or 15 to 20 milliamps on a 12-volt actuator is a typical draw. In sleep mode, it'll do less than 1 milliamp at 12 volts and less than 2 at 24. So we're going down quite a bit, and it allows us to have the actuator sit on the bus actively without worrying about it drawing a lot of power from your power supply, battery, whatever you want to call it.
Okay. All right. So sticking with that, with the current theme. So what earlier you were talking about current monitoring and also how that could help stop movement. The question is, what are what would be some limitations of using that current monitoring or current sensing to stop movement in a overload type of situation?
Limitations of load sensing. Well, it depends on what you're using it for, really. the problem with it is that you have to be able to see what's happening on the actuator if it were to trip mid-stroke. And typically, if you do have that trip happen in the middle of a stroke, as a safety precaution, it will require you to reverse the actuator in the direction that it was traveling to get it to go forward again, simply because it will want to stop. You know, let's just say say a guy gets his hand stuck somewhere and it causes you to trip the current of the actuator and it stops, which is great. You know, it's saving whoever's arm or whatever it may be that's happening from breaking or happening to it. Caution is to have you reverse it before you go forward again. So some people see that as something, a hurdle to get around when that system trips. But it's designed to stop in case of an overload in general. So we don't see those trips as a nuisance trip, and it should be something that should bring the user or whoever is controlling the system. It should bring their attention to it anyway. So that would be an issue that some people would see where that tripping would happen and they'd have to intervene, right? But it's an overload feature. If you were designing the actuator for the application properly, you'd almost never see that. And typically, you can use it at end of stroke too to kind of cut off your power, and it's not typically a bad thing to do that at the end of stroke. However, it's not going to hurt your electronics, really, is what I'm trying to say. But if you're running your actuator into a hard stop to spike that current and shut it off, I mean that's going to be an issue for the kernels of the actuator. Typically not a great application, but it will work. So it's a fail-safe, I guess is the best way to say this. It's a feature that allows you to not break anything when the loading scenario goes. Still want to control the actuator as best as possible, which is why we included all the other control features.
Okay. All right. So here's a specific question about one of the products here that was mentioned. Does the I'm not sure if I'm saying this right. Does the Electrac have the internal switching and the CAN bus?
Yeah. So Electrac is kind of like our brand of actuator. Internal switching or low-level switching or an integrated H-bridge and CAN bus, yes, those are both features we have on that actuator. So what that gives you is low-level switching, which is great for, I guess, controlling the actuator, not having to worry about high power draw. It also gives you dynamic braking circuits. The CAN bus, of course, gives you all those lovely features I was talking about earlier with controlling the actuator's function.
Okay. All right, so we're getting close to the end here. Let's see how many more we can get in. But here's one more question: how do the limit switches work on the PPA actuators?
PPA actuators utilize a cam system. So take apart the back of an actuator. It has a rotating cam that over a stroke will toggle a mechanical limit switch. It's a micro switch inside that will toggle and hit end of stroke. So they're not switches inside of the actuator on the tube. It's in the rear of the actuator in a gearing assembly, driven off the gearing.
Okay.
PPA is a legacy product from us, but still very relevant with again modular controls, and it kind of speaks the same story as wanting to integrate electronics. So good question.
Okay. All right, good. So maybe looks like maybe we can hit maybe one more as we're getting close to the end here. But so here's kind of a general question. But what would be required to run an actuator on a CAN bus network?
A couple things. You have to wire it a certain way, and this is going to be more familiar to people that have worked with it before. But you use a two-wire system, which is simple enough. But the longest leg of that two-wire system has to be terminated with resistors, and that's simply to allow the network to be as fault tolerant as it is. And aside from that, you'll have to have your nodes on the bus, whether those be actuators or other devices. And the third thing, and arguably the most important thing, is a controller for the entire bus, whether that be ECU in a vehicle, right, and control the engine or related functions, or whether it be a laptop computer, or whether it be an interfacing device to switch it over from Ethernet IP to CAN bus communication, there needs to be a microcontroller, essentially telling everything where to go, just like in a home computer. So one control box, the wiring, and the things being controlled. Aside from power, right, those are the three things you need in order to have a CAN bus system function.
Okay. All right, good enough. I think that brings us to the end here. We're done with the questions. We're done with our time here. I think we've hit all of them. We may have missed a few, but just to kind of wrap up here, some things. I just want to remind everyone that after this webinar is finished, you can find this presentation online there at designworldonline.com. Also, if you'd like to tweet about any of the content of this webinar, you can do so using that hashtag DWWebinar. You can connect with Design World through our various social media platforms there, including Facebook and LinkedIn and Twitter, Google+, Pinterest, YouTube as well. Also, we can discuss this webinar on engineeringexchange.com. Also, you can, all of our contact info is there, so you can touch base with either Travis or Håkan or me if you want to, with any follow-up at all. So with that, I want to thank you guys, both Håkan and Travis, for your time today and for your presentation, and thank everybody else who joined us here today. I hope you found it useful. And once again, thanks, guys. Thanks, everyone.
Thank you.
Thank you, Miles.
Happy to be here.
Okay, and hope everyone has a good rest of the day. All right, take care.